Hello and welcome to the second lecture on differential equations. So in the previous lecture we've been talking about the generalities of differential equations. We've been talking about what a differential equation is. We've been talking about how to get a differential equation by removing the constant from a function, and we've seen some jargon of differential equations just to get used to the language. Now, for this lecture, I've also prepared some lecture notes, and you can find them in the description of the video. So I think it's time to get started. Today we're going to solve our first differential equations, so it's going to be pretty exciting. So let me start by telling you what the most general form of a differential equation is. So let me call it psi. I'll explain you later what psi means. And the psi of x, y, where y is a function of x, y prime, and all the other derivative terms, all the way up to the nth derivative of the function, equals 0. Now, this psi represents all the operations, rational, irrational, and transcendental, we've done to arrange the equation in the following way. So everything is on the left-hand side, and that equals to 0. This is called the non-normal form of a differential equation. Then if we can isolate the nth derivative of y, and we can put this equal to, for example, theta. Theta is similar to psi, but now we have the nth derivative of y on the other side of the equation, so x, y, and all these other terms, all the way up to, not y to the n, y to the nth derivative of y is here. So we have the previous derivative, so the term y, the n minus 1th derivative of y. This is called a differential equation in normal form. Now, today we're going to talk about a very specific set of differential equations. And but before doing that, I'll explain you. Here's an example of how to get a normal equation. So this is trivial, so you'll be able to do that. It's just fine. Y prime minus y plus x minus 1 equals 0. Here's our equation, and we need to find, this is written in non-normal form. To get the normal form, the highest term is y prime, so y prime equals to y minus x plus 1. And that's, of course, trivial. Here's another example, so I'll show you what this is. This was absolutely trivial, but trivial doesn't mean it's not necessary in order to learn the subject. Y prime plus xy plus x squared equals 0. And in this equation, we have to get to the normal form of the equation. This is the non-normal form. We need to isolate y prime. So how do we do it? We transfer all this term to the other side, and we remain with this. We divide both sides by x plus y, and we get the following. Y prime equals 2. We put a minus sign here, minus x, y plus x, over we also have x plus y, and now, as you can see, this is xy plus x squared. I can factor out x, and I get y plus x. Here's our x, and the minus sign, because this is plus plus, so on the other side of the equation it's minus, divided by x plus y. Now, of course, we could simplify this, but we have to say that x plus y cannot be equal to 0. So y cannot be equal to minus x if we get to the normal form of the equation. But we get a kind of contradiction, because here it says y prime equals minus x, and here it says y is not equal to minus x. So, of course, we shouldn't simplify this this term here, But of course, y equals minus x does satisfy the differential equation, because if we differentiate y, this function, we get minus 1. We put y here, and you can do that. That's an exercise for you. You can put this into the differential equation, and you'll see that x plus y does indeed satisfy the differential equation. Now, it's very important to keep track of all the functions that satisfy the differential equation. So you should do all these steps and be sure what cannot be equal to 0, because it's in the denominator and all that stuff. It's very important. Then, for example, if you turn the equation into normal form and there are some solutions excluded from what you've get, it doesn't necessarily mean that those solutions are no solution to the previous differential equation, and we'll see that in other examples. Now we get to the integration of first order ODEs in normal form. So what is a first order ODE? We said that the highest derivative appearing in the equation is the first derivative. So we can write it in normal form. So y prime equals 2. We can always use the symbol psi, because it always looks cool, I have to say. And we have x, we have y, and there are no other higher derivative terms. So this is first order, and this is a first order differential equation, and it's also a first degree differential equation. So keep that in mind. We have this equation here. Now we're going to solve a special case of this equation. So let me just get rid of this. And this specific case is called a separable differential equation. A separable differential equation means that this right-hand side here can be written as the product of two functions. A function m, the name is arbitrary, as you might have guessed, m of x, times another function that I call it m of y. Now, what's the important thing about this? Is a special case. Not every function that's first order and written in normal form obeys to this equation, because this is a special case where you can just separate x and y. So we have only a function of x that multiplies only a function of y. Even though y is a function of x, I'm not talking about that, but you can separate the x variable and the y variable, even though they're connected, they're dependent on each other. This is called a separable differential equation, and there are two special cases, because, for instance, when ny there is no y term in the equation, we get a function y prime is only a function of x. Whereas if there is no term on the right hand side of the equation, then y prime is only a function of y. And this is a map of a separable differential equation, the most general case. We'll see next time how to solve it, and the two specific cases. So today we're going to focus on the first case. Now you may say it's obvious, but it's always better to start from the basis concepts and then just grind to more advanced things, even though this is very simple, and you see how simple it is. So today we're focusing on the first case, so let me get the examples. Here's our first example, and we're going to solve a differential equation of this form. So it can be performed, as you will see, by direct integration. So y prime, here's our function, y prime equals 2 cosine of x plus 2x. Okay. As always, the Leibniz notation is always, let's say, well accepted because it's very simple and a neat way to solve differential equations. dy by dx equals to cosine of x plus 2x. Now, you see that this corresponds to an equation of this type. So the right-hand side is only, there are only x involved in the right-hand side of the equation. So what can we do? Well, just, I'd say multiply by the differential dx because it's rigorous to do that, and then integrate both sides by or if you like, you can integrate now both sides by x, and this gets the integral of dy, but it doesn't really matter. So the integral of dy equals to, bring x to the other side, cosine of x plus 2x dx. Okay guys, sorry about that, no more distractions from now on. So we have to integrate this. So the integral of y is simply y. Now you may say, why aren't you putting the constant, because this is an indefinite integral? Well, because we have a constant on the right-hand side, we have another constant on the right-hand side. Can we simplify them? No, because they're two different constants. They could also be the same, but in general, they're not. So we can bring them all to one side. For example, the right-hand side, we sum them, and the sum is our general constant. So let's do this integral. So the integral of cosine of x. What is the integral of cosine of x? Obviously, it is sine of x. And what's, because the derivative of sine is cosine, obviously, what's the integral of 2x? X squared divided by 2 times 2. So this is simply plus x squared plus our general constant c, and this function satisfies the differential equation. The derivative of this function simply equals this function. So this is not complicated at all. It's trivial, but as I said, trivial, it's important. Now let's do another example. This is probably a bit more difficult than the previous example. Now, well, before doing this example, I want to notice something very interesting. If we take into account the general form, normal form of our differential equation, we can simply integrate both sides with respect to x. And on the right-hand side, we get y, and on the right-hand side, on the left-hand side, sorry, we get y, and on the right-hand side, we get the integral of this function of x. So if you have this differential equation, this is how to solve that differential equation. So this is clear. I mean, it's not too complicated. So we're going to solve two more examples, another trivial example and then a more complicated example. So, well, I'm not going to erase this because it's what we're doing. So the example is y prime equals to x squared minus 5x. Then we have to add a 6. Here's my differential equation. Now, you might recognize that these differential equations are indeed the expression for the derivative. So, of course, integrating is the operation to do to get back to the original function without manipulating the equation. But that's for now, because from the next example, things are going to change. But today we'll keep things simple. So we can integrate both sides with respect to x. We get y plus the constant, and we consider the constant on the right-hand side. We get those two constants together. The integral of this is x cubed over 3 minus 5 over 2x squared plus 6x. Now you should be familiar with how to do these trivial integrals. And this is the expression for our function y. And that's the solution to the differential equation. Now it's time to get to the example, the most important example of today's video. And the important thing about differential equation is not how to solve them, it's how to arrange them in a way that you can solve, because you recognize what equation is. So x squared y prime minus x equals 4. And okay, here's the example. I think it's the last example. So, well, this is kind of similar to this, but it's not quite the same because we have an x squared multiple of our derivative. So how can we rearrange? This is obviously not written in normal form. We also have a 4 on the right hand side. So we need to rearrange the equation. So we move x to the other side of the equation. So y prime, we also have an x squared here, equals to 4 plus x. Now, to isolate y prime, we can divide both sides by x squared. And we are going to do so right now. But now there's something that has to be said. X cannot be equal to 0, of course, because if x were 0, then we would have a 0 in the denominator, and that is not allowed. So keep track of all the things that are defined and aren't. Now, here we have the function. That's also a trivial thing to do. We need to integrate both sides, so y equals to this integral. And we can also split this integral into two integrals because we have a fraction here, a sum on the numerator, so we can split it up into two pieces. So we have the first 4 divided by x squared plus x divided by x squared, so simply 1 over x. Now, guys, we need to solve the first one. Well, the first one, we can rewrite this x squared. First, we can bring the 4 outside because it's a constant multiple. And we can write x in the denominator squared as x to the minus 2. And we can do the integration. So the integral of this is x to the minus 1, because we have to add plus 1 times minus 1. So this becomes minus 4x to the minus 1. And now let's do the second integral plus the natural log of x plus c. Don't forget the absolute value. Remember, whenever you integrate 1 over x, you have to put the absolute value here. And this is the solution. We can write this into a more elegant way if we desire to do it. Here's the solution. Now, this is a very important example because today it's all very simple and trivial, but I want you to get started with the topic. So, okay, guys, so I'm back again. So we are talking about this constant. So there's an interesting thing we could do with this constant, and it will turn out to be very useful later on. So instead of writing, I'm calling it C1, and I'll explain you why. Because we can get rid of this absolute value of x in a very clever way. We can call C1 is an arbitrary constant, any real number, so it could be any real number. But we can put this equal to another constant, mainly the natural log of a constant c. Why can we do that? Well, because c1 can be any natural number, as I said, and the natural log function covers all the real numbers. So we can do this substitution here, and it turns out to be very interesting because now, thanks to the properties of logarithms, we can bring these two arguments of the two logs together, and we can write this in the following way, because this is a sum of logarithms, so we can write this as natural log of the constant c times the absolute value of x. But now, what's even more interesting is that the absolute value of x, well, we can get rid of it, because if we choose c greater than 0 and x is greater than 0, then this quantity is obviously positive. But when we choose c to be less than 0, we require x less than 0. Or better, when x is greater than 0, we put the constant greater than 0. When it's less than 0, we put the constant less than 0. And in this way, we can get rid of the absolute value, because this quantity here is always positive. So it turns out to be very useful when we solve differential equation. Not much in these cases here. It obviously simplifies this equation, not very much. But when we have y inside the natural log with the absolute value, then if we want to isolate y, this trick turns out to be very interesting. And we're always going to update this constant to get the solution. So I'll see you in the next video on differential equation. Thank you so much for watching.